In the depths of space, 2.5 million light-years away, lurks something extraordinary. Something so massive, so violent, so utterly incomprehensible that it defies every assumption we have about the universe. At the heart of our nearest galactic neighbor, the Andromeda Galaxy, sits a monster that makes our own Milky Way's central black hole look like a gentle giant. But here's what's absolutely mind-blowing about this cosmic behemoth. While we've spent decades studying our own galactic center, peering through dust clouds and mapping the dance of stars around our supermassive black hole, Andromeda's core holds secrets that could completely reshape our understanding of how galaxies live, breathe, and die. I'm about to take you on a journey to the most violent place in our local group of galaxies. We're going to explore a region where space and time bend beyond recognition, where matter gets shredded into oblivion, and where the very fabric of reality breaks down. By the end of this exploration, you'll understand not just what lies at Andromeda's heart, but why this knowledge is crucial for predicting the ultimate fate of our own galaxy. Because here's the thing that most people don't realize. In approximately 4 billion years, our Milky Way is destined to collide with Andromeda in one of the most spectacular cosmic events imaginable. And when that happens, these two galactic monsters at our respective centers are going to meet in a gravitational dance that will reshape both galaxies forever. So, what exactly are we dealing with here? What kind of cosmic entity could command an entire galaxy of over 1 trillion stars? The answer begins with understanding just how different Andromeda is from our own galactic home. While the Milky Way contains somewhere between 200 and 400 billion stars, Andromeda dwarfs us with over 1 trillion stellar inhabitants. It stretches across 220,000 light-years, making it significantly larger than our galaxy's 100,000 light-year span. But size is just the beginning of this story. At Andromeda's core sits a supermassive black hole designated as P2. This isn't just any black hole. We're talking about a gravitational monster that tips the scales at somewhere between 100 and 200 million times the mass of our Sun. To put that in perspective, if our Sun were a marble, this black hole would be larger than Mount Everest, but packed into a space smaller than our solar system. But mass alone doesn't tell the whole story. What makes P2 truly fascinating is how it compares to our own galactic center. Sagittarius A star, the supermassive black hole at the heart of the Milky Way, weighs in at about 4 million solar masses. That means Andromeda's central black hole is potentially 50 times more massive than our own. It's like comparing a house cat to a full-grown tiger. This massive difference raises profound questions that keep astrophysicists awake at night. How did Andromeda's central black hole grow so much larger than ours? What does this tell us about the different evolutionary paths these galaxies have taken? And most importantly, what happens when these two cosmic titans eventually meet? The environment around P2 is nothing short of extraordinary. Imagine a region of space where the gravitational pull is so intense that it warps the very fabric of space-time. Stars that venture too close don't simply fall in. They get stretched and torn apart in a process called spaghettification, their material forming long streams of superheated gas that spiral inward at tremendous speeds. This accretion process creates one of the most energetic phenomena in the known universe. As matter falls toward the black hole, it heats up to temperatures of millions of degrees, glowing brighter than entire stars. The magnetic fields generated by this swirling plasma create jets of particles that shoot out from the black hole's poles at nearly the speed of light, extending for thousands of light years into intergalactic space. But here's where things get really interesting. Unlike some supermassive black holes that are actively feeding and creating brilliant quasars visible across the universe, P2 appears to be relatively quiet right now. It's what astronomers call a dormant or inactive galactic nucleus. This doesn't mean it's harmless. It just means it's not currently devouring massive amounts of material. This dormant state actually makes P2 more similar to our own Sagittarius A star, which is also relatively quiet. Both black holes occasionally flare up when they capture passing gas clouds or unfortunate stars, but they're not the ravenous monsters we see in some distant galaxies. This similarity raises intriguing questions about the relationship between galactic evolution and central black hole activity. The region immediately surrounding P2 is populated by some of the oldest stars in the Andromeda Galaxy. These ancient stellar inhabitants have been orbiting the galactic center for billions of years, their paths slowly decaying as they lose energy to gravitational waves. Some of these stars follow incredibly elliptical orbits that bring them dangerously close to the black hole before flinging them back out to safer distances. Studying these stellar orbits has provided crucial insights into the black hole's properties. By measuring how fast stars move as they whip around P2, astronomers can calculate the central mass with incredible precision. It's the same technique used to study our own galactic center, but Andromeda's greater distance makes these measurements significantly more challenging. What's particularly fascinating is the discovery of what appears to be a double nucleus structure in Andromeda's core. For years, astronomers thought they were seeing two separate concentrations of stars, possibly indicating a binary black hole system. The implications would have been staggering. Two supermassive black holes orbiting each other would create gravitational waves so powerful they could be detected across the observable universe. However, more detailed observations revealed a different picture. What appeared to be two nuclei is actually a single, asymmetric structure. The central region of Andromeda contains a disk of older red stars that creates this double-peaked appearance when viewed from our angle. It's like looking at a donut from the side and seeing two bright edges instead of recognizing the circular structure. This stellar disk spans roughly 5 light-years across and contains millions of stars, many of them red giants nearing the end of their lives. The disk is tilted with respect to the main galactic plane, suggesting a complex history of interactions and possibly past galactic mergers that helped shape Andromeda's current structure. The presence of this stellar disk also tells us something crucial about the black hole's feeding habits. For such a structure to exist and persist, P2 must have been relatively quiet for extended periods. A highly active black hole would disrupt these stellar orbits through powerful outflows and radiation pressure. But perhaps the most mind-bending aspect of P2 is what it reveals about the future collision between Andromeda and the Milky Way. When two galaxies merge, their central supermassive black holes don't immediately combine. Instead, they begin a cosmic dance that can last for hundreds of millions of years. Initially, the two black holes orbit each other at distances of thousands of light years. Over time, gravitational interactions with surrounding stars and gas cause their orbits to decay. They spiral closer and closer together, eventually reaching distances where gravitational wave radiation becomes the dominant mechanism for losing orbital energy. In the final moments before merger, when the two black holes are separated by just a few times their event horizon radii, they're moving at significant fractions of the speed of light. The gravitational waves they emit carry away enormous amounts of energy, causing them to spiral together even faster in what's called a chirp pattern. The actual collision and merger happens in mere milliseconds, but it releases more energy in gravitational waves than all the stars in the observable universe emit in light during the same time period. The resulting black hole, formed from the combination of P2 and Sagittarius A star, would have a mass approaching 200 million times that of our Sun. This merged black hole would likely receive a gravitational wave recoil kick that could send it careening through the newly formed galaxy at speeds of hundreds or even thousands of kilometers per second. Depending on the masses and spins of the original black holes, this kick could be strong enough to eject the merged black hole from the galaxy entirely, leaving the new galactic structure without a central, massive anchor. The implications of this potential ejection scenario are staggering. A galaxy without its central supermassive black hole would behave very differently than what we observe today. The gravitational influence of these massive objects helps regulate star formation across the entire galactic structure. Without this central anchor, the newly merged galaxy could undergo dramatic changes in its stellar birth rate and overall architecture. But let's step back and examine what makes P2 so fundamentally different from other supermassive black holes we've discovered across the cosmos. Most of the monster black holes we detect in distant galaxies are actively feeding, creating some of the brightest objects in the universe as they devour surrounding material. These active galactic nuclei can outshine their entire host galaxies, visible across billions of light years. P2's relative quietude makes it far more challenging to study, but also more representative of what most supermassive black holes are actually doing right now. The universe's most dramatic feeding frenzies happened billions of years ago when galaxies were younger and gas-rich. Today, most central black holes have settled into a more sedate existence, occasionally snacking on passing material, but not gorging themselves like their ancient counterparts. This dormant state doesn't mean P2 is completely inactive. Sophisticated observations have detected subtle signs of ongoing accretion. X-ray emissions from the galactic center indicate that hot gas is still falling into the black hole, just at a much reduced rate compared to the cosmic feeding frenzies of the past. These faint signatures require our most advanced space-based telescopes to detect, pushing the limits of current observational technology. The structure surrounding P2 reveals clues about Andromeda's violent past. The galaxy shows clear signs of having cannibalized smaller neighboring galaxies over billions of years. Each of these ancient mergers would have disrupted the central region, potentially feeding material to the growing black hole and reshaping the stellar populations we observe today. Evidence for this cannibalistic history comes from studying the chemical composition and ages of stars in different regions of Andromeda. Astronomers have identified streams of stars with distinct properties that likely originated from smaller galaxies that were torn apart and absorbed. These stellar streams wrap around Andromeda like cosmic scar tissue, permanent reminders of the galaxy's predatory past. The discovery of these merger remnants suggests that P2 may have grown through a series of smaller black hole mergers rather than steady accretion alone. Each time Andromeda consumed a smaller galaxy, it also inherited that galaxy's central black hole. These smaller black holes would eventually spiral into P2, adding their mass to the growing monster at Andromeda's heart. This growth mechanism has profound implications for understanding how supermassive black holes reach such enormous sizes. The traditional model assumed these objects grew primarily by accreting gas and dust from their surroundings. But mounting evidence suggests that mergers between black holes may be equally important, especially for the larger specimens like P2. The timing of these ancient mergers also influences what we might expect during the eventual Milky Way Andromeda collision. Computer simulations suggest that galaxies with recent major merger histories behave differently during subsequent interactions. Andromeda's complex structure, shaped by its cannibalistic past, could lead to unexpected dynamics when it encounters our galaxy's more pristine spiral architecture. One of the most intriguing aspects of studying P2 is how it challenges our understanding of the relationship between galaxies and their central black holes. Observations across the universe have revealed a tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. This relationship suggests a fundamental connection between galactic evolution and black hole growth. But Andromeda's central black hole appears to be somewhat overmassive compared to what this relationship would predict. P2's enormous size relative to Andromeda's bulge hints at a more complex evolutionary history than the standard models assume. Perhaps the galaxy's merger-rich past allowed its central black hole to grow beyond the typical limits imposed by feedback processes. This overmassive nature has implications for the types of phenomena we might observe as P2 becomes more active in the future. A larger black hole can potentially accrete material more efficiently and create more powerful outflows when it does begin feeding. If the upcoming galactic collision provides P2 with fresh fuel, we might witness one of the most spectacular active galactic nuclei events in our local cosmic neighborhood. The magnetic field environment around P2 adds another layer of complexity to this already mind-bending system. Like all supermassive black holes, P2 is surrounded by twisted magnetic field lines that channel the flow of charged particles. These fields can store enormous amounts of energy, occasionally releasing it in dramatic flares that heat surrounding gas to millions of degrees. Recent observations have detected polarized radio emissions from Andromeda's core, indicating the presence of these magnetic fields and their interaction with relativistic particles. The magnetic field structure appears to be more complex than what we observe around our own galactic center, possibly due to P2's larger mass and the more chaotic environment created by past merger events. Understanding these magnetic phenomena is crucial for predicting how P2 will behave during the upcoming galactic collision. Magnetic fields can influence how efficiently material falls into the black hole and determine the power and direction of any resulting jets. A more powerful magnetic field environment could lead to more dramatic fireworks when the collision provides fresh material for P2 to consume. The event horizon of P2 represents one of the most extreme environments imaginable. This boundary, located roughly 300 million kilometers from the black hole's center, marks the point of no return, where space and time become so distorted that even light cannot escape. Anything crossing this threshold is doomed to fall toward the singularity at the black hole's heart, where our current understanding of physics completely breaks down. Near the event horizon, time dilation effects become so extreme that processes we observe from a distance appear to slow to a crawl. A hypothetical observer falling toward P2 would experience time normally, but to anyone watching from a safe distance, they would appear to freeze at the event horizon. Their image redshifted into invisibility as the black hole's gravity stretches light to longer and longer wavelengths. The tidal forces near P2's event horizon are beyond comprehension. Any object approaching too closely would be stretched vertically and compressed horizontally by the difference in gravitational pull between its head and feet. For P2, this spaghettification process would begin well outside the event horizon itself, turning unfortunate stars into long streams of plasma before they ever cross the point of no return. These extreme conditions make P2 a natural laboratory for testing the most fundamental theories of physics under conditions impossible to recreate on Earth. The interaction between quantum mechanics and general relativity near the event horizon could reveal new insights into the nature of space, time, and matter itself. Some theoretical physicists speculate that the information paradox associated with black hole evaporation might be resolved by phenomena occurring in these extreme environments. As we peer deeper into the mystery of what lies at Andromeda's center, we're forced to confront the limitations of our current observational capabilities. P2 sits at the edge of what our most advanced telescopes can resolve, requiring innovative techniques and international collaboration to extract meaningful data from the faint signals reaching Earth across 2.5 million light-years of intergalactic space. The quest to understand P2 has pushed astronomical technology to its absolute limits. Traditional optical telescopes struggle to penetrate the layers of dust and gas that shroud Andromeda's core, while radio observations provide only glimpses of the magnetic chaos surrounding the black hole. But recent breakthroughs in adaptive optics and space-based interferometry are beginning to unveil secrets that have remained hidden for decades. One of the most remarkable discoveries emerged from years of painstaking observations using the Hubble Space Telescope. By carefully tracking the motion of individual stars near Andromeda's center, astronomers detected something completely unexpected. The stars weren't behaving as they should around a single massive object. Instead, Their orbital patterns suggested the presence of additional gravitational influences that couldn't be explained by P2 alone. This led to the startling realization that Andromeda's core might harbor not just one supermassive black hole, but potentially multiple massive compact objects. While the double nucleus mystery had been solved, the gravitational dynamics revealed something far more intriguing. There could be intermediate mass black holes, each weighing thousands of times more than our Sun, orbiting within the broader gravitational sphere of P2's influence. These smaller black holes would be the remnants of past galactic cannibalism, the former centers of dwarf galaxies that Andromeda consumed over billions of years. Rather than being immediately absorbed into P2, they could have settled into stable orbits, creating a complex gravitational ecosystem unlike anything we observe in our own galactic center. The implications of this multi-black hole system are staggering. Each of these intermediate mass objects would generate its own accretion disk when it captures passing material. The interactions between these multiple feeding zones could create a cascade of gravitational disturbances, occasionally flinging stars at tremendous velocities, or triggering coordinated flares of high-energy radiation. But here's where the story takes an even more dramatic turn. Computer simulations of the eventual Milky Way Andromeda collision suggest that these multiple black holes could fundamentally alter the merger process. Instead of a simple two-body gravitational dance between our galaxy's central black holes, we might witness a chaotic multi-body interaction that defies our current predictions. The energy released during such a complex merger could be orders of magnitude greater than previously calculated. Gravitational waves from multiple black hole interactions occurring simultaneously would create interference patterns that could be detected by future space-based gravitational wave observatories. These signals would provide an unprecedented view of the most violent gravitational events in the local universe. Recent theoretical work suggests that P2's enormous mass might not be the result of steady growth or even simple mergers. Instead, it could have formed through a process called hierarchical assembly, where multiple generations of black hole mergers created increasingly massive objects. Each merger would have released tremendous amounts of energy, potentially explaining some of the unusual structural features we observe in Andromeda's central regions. This hierarchical growth model predicts that P2 should be spinning at a significant fraction of its theoretical maximum rate. A rapidly rotating supermassive black hole creates what physicists call a Kerr spacetime, where the fabric of space itself is dragged around the black hole in a phenomenon known as frame dragging. This rotation would influence everything from the shape of nearby stellar orbits to the direction and power of any jets that might form during active feeding periods. Measuring P2's rotation rate represents one of the holy grails of current observational astronomy. The task requires detecting incredibly subtle effects on the motion of nearby stars and gas clouds. Advanced techniques using very long baseline interferometry are beginning to provide hints, but definitive measurements remain tantalizingly out of reach with current technology. The environment immediately surrounding P2 contains some of the most exotic matter in the known universe. The intense gravitational field creates conditions where quantum effects might become macroscopically visible. Virtual particle pairs, normally too short-lived to observe, could be separated by the extreme tidal forces, with one particle falling into the black hole, while the other escapes as Hawking radiation. This quantum evaporation process, predicted by Stephen Hawking, suggests that even the most massive black holes are slowly losing mass by emitting radiation. For an object as massive as P2, this evaporation rate is incredibly slow, requiring more time than the current age of the universe to lose even a tiny fraction of its mass. Yet this process might be detectable through its influence on the temperature and density of surrounding gas clouds. The discovery of exotic matter states near P2 could revolutionize our understanding of fundamental physics. Some theoretical models predict the formation of strange matter or quark-gluon plasmas in the extreme conditions just outside the event horizon. These states of matter existed only in the first microseconds after the Big Bang and might be recreated in the gravitational furnace surrounding supermassive black holes. Perhaps the most mind-bending aspect of P2 involves its relationship with the very structure of space-time itself. Einstein's equations predict that the presence of such a massive object creates what physicists call a gravitational well so deep that it fundamentally alters the geometry of the universe in its immediate vicinity. Space becomes curved to such an extreme degree that parallel lines can meet, and straight lines can form closed loops. This warping of space-time creates observable effects that extend far beyond the black hole itself. Light from distant stars is bent and focused as it passes near P2, creating gravitational lensing effects that can magnify and distort the images of objects lying directly behind the black hole from our perspective. These lensing signatures provide another tool for measuring P2's mass and spin, though the required precision pushes current observational capabilities to their limits. The gravitational time dilation near P2 means that clocks would run slower as they approach the black hole. An observer stationed near the event horizon would age more slowly than someone watching from a safe distance. This effect, while imperceptible for everyday purposes, becomes significant enough to measure in the extreme gravitational environment surrounding supermassive black holes. As we attempt to map the immediate vicinity of P2, we encounter the fundamental limits imposed by the uncertainty principle. The act of observation itself becomes problematic when dealing with objects whose gravitational influence extends across light years, while their essential features are concentrated within a region smaller than our solar system. Each photon we collect carries information that has been fundamentally altered by its journey through the warped space-time surrounding the black hole. The magnetic field lines threading through P2's environment create a complex web of electromagnetic forces that can accelerate particles to relativistic speeds. These cosmic particle accelerators operate on a scale that dwarfs anything humans have constructed, generating particle beams with energies millions of times greater than our most powerful colliders. The resulting high-energy radiation creates a faint but detectable signature that helps astronomers map the invisible magnetic architecture surrounding the black hole. Deep within Andromeda's core, beyond the reach of any current or planned observatory, lies the ultimate mystery. At the very center of P2, general relativity predicts the existence of a singularity, a point where density becomes infinite and the normal laws of physics cease to apply. This singularity represents the ultimate boundary of human knowledge, a place where space and time themselves might break down into something entirely beyond our current understanding. The information that falls past P2's event horizon becomes permanently disconnected from the observable universe, at least according to classical physics. Yet quantum mechanical considerations suggest that this information might not be truly lost, leading to one of the most profound paradoxes in modern theoretical physics. The resolution of this information paradox could require a fundamental revision of our understanding of reality itself. As gravitational wave astronomy continues to mature, P2 and its potential companion black holes will become prime targets for next-generation space-based detectors. These instruments will be sensitive enough to detect the subtle ripples in space-time created by objects orbiting close to massive black holes, providing an entirely new window into the dynamics of these extreme environments. The eventual collision between our galaxies will transform P2 from a relatively quiescent object into one of the most active and energetic phenomena in the local universe. The massive reservoir of gas and dust that will be stirred up during the galactic merger will provide fuel for a feeding frenzy that could last for hundreds of millions of years. During this period, P2 could become visible across the entire observable universe as one of the brightest quasars ever recorded. This transformation will offer astronomers an unprecedented opportunity to study supermassive black hole physics in real time. The gradual increase in P2's activity as the collision approaches will allow us to observe the transition from dormant black hole to active galactic nucleus, providing crucial insights into the mechanisms that trigger these cosmic feeding events. The legacy of P2 extends far beyond its role in the upcoming galactic collision. As one of the most massive black holes in our local cosmic neighborhood, it serves as a crucial calibration point for understanding how these objects form and evolve across cosmic time. The lessons learned from studying P2 will inform our interpretation of similar objects detected in the distant universe, helping us piece together the complete story of how supermassive black holes have shaped galactic evolution throughout cosmic history. But what happens when we try to peer even deeper into this cosmic abyss? What secrets might be revealed if we could somehow journey to the very edge of P2's event horizon? The answer lies in understanding phenomena so bizarre that they challenge our most fundamental assumptions about reality itself. Recent theoretical breakthroughs have suggested that the environment around supermassive black holes like P2 might host some of the universe's most exotic phenomena. Consider this. The immense gravitational field creates regions where the normal flow of time becomes so distorted that cause and effect relationships begin to break down. Near the event horizon, quantum fluctuations that normally cancel each other out might become amplified into macroscopic effects, visible across thousands of light years. These quantum amplification zones could explain some of the mysterious high-energy emissions detected from Andromeda's core. When virtual particles are separated by extreme tidal forces, with one falling into the black hole while the other escapes, the result is a steady stream of real particles emerging from apparently empty space. This process, known as Hawking radiation, suggests that P2 is slowly evaporating, though at a rate so glacial that it would take longer than the age of the universe to lose even a fraction of its mass. But here's where things get truly mind-bending. The information carried by particles falling into P2 doesn't simply disappear. According to the holographic principle, all the information about everything that has ever fallen past the event horizon might be encoded on the black hole's surface, like a cosmic hard drive. This two-dimensional surface somehow contains all the three-dimensional information about the black hole's interior, suggesting that our entire perception of spatial dimensions might be fundamentally flawed. The implications stretch far beyond theoretical physics. If the holographic principle is correct, then P2's event horizon contains the complete history of everything it has ever consumed. Every star, every planet, every particle of gas that has fallen into this cosmic monster over billions of years might still exist as information patterns encoded on this ultimate boundary between the known and unknowable. This information storage mechanism could make P2 something like a cosmic library, containing the compressed histories of entire civilizations that might have existed in the galaxies Andromeda has consumed. While we can never retrieve this information using any known physical process, its mere existence challenges our understanding of what it means for something to be truly lost or destroyed. The study of P2 has also revealed unexpected connections between black hole physics and the fundamental structure of space itself. Recent observations suggest that the vacuum of space around supermassive black holes might not be as empty as we once believed. Instead, it could be filled with a seething foam of virtual particles and quantum fields that become visible under the extreme conditions near the event horizon. This quantum foam creates a kind of cosmic static that interferes with our observations, making it incredibly difficult to study the immediate vicinity of P2 with precision. Advanced signal processing techniques, originally developed for analyzing gravitational waves, are now being adapted to filter out this quantum noise and reveal the subtle signatures of exotic physics occurring in the black hole's immediate environment. The magnetic field structure around P2 exhibits properties that push the boundaries of our understanding of plasma physics. The field lines become so twisted and concentrated that they can store energies equivalent to the total output of entire star clusters. When these magnetic structures occasionally reconnect and release their stored energy, they create gamma ray bursts that can be detected across intergalactic distances. These magnetic eruptions might explain some of the periodic brightening events observed in Andromeda's core over the past century. While P2 is generally dormant compared to actively feeding black holes, it still experiences occasional flares when magnetic field lines snap and reconfigure. These events provide brief glimpses into the violent processes that will become commonplace once the galactic collision begins feeding fresh material to this cosmic monster. The gravitational environment around P2 creates natural laboratories for testing some of the most speculative theories in modern physics. String theory predicts the existence of extra dimensions beyond the three spatial dimensions we experience in everyday life. The extreme curvature of space-time near supermassive black holes might allow these hidden dimensions to become accessible, creating observable effects that could revolutionize our understanding of reality's fundamental structure. Some theoretical models suggest that P2 could be connected to other regions of space-time through microscopic wormholes that thread through these extra dimensions. While these connections would be far too small to allow travel or communication, they might create subtle correlations between events occurring near different black holes across the universe. Detecting these correlations would provide the first direct evidence for the existence of extra dimensions. The study of stellar orbits around P2 has revealed another layer of complexity in this already bewildering system. Some stars follow paths so eccentric that they spend most of their orbital period in the relatively safe outer regions, only to plunge deep into the black hole's gravitational well once every few thousand years. During these close approaches, these stars experience gravitational forces strong enough to strip away their outer layers, creating spectacular displays of stellar cannibalism. These periodic feeding events contribute to P2's gradual growth, while also providing astronomers with opportunities to study matter under extreme conditions. The stripped stellar material forms temporary accretion disks that glow brilliantly in X-rays before disappearing into the black hole. By timing these events and measuring their intensity, researchers can map the three-dimensional structure of space around P2 with unprecedented precision. The discovery of these tidally disrupted stars has also revealed the presence of a population of hypervelocity objects in Andromeda's core. When binary star systems venture too close to P2, the black hole's gravity can capture one star while flinging the other away at speeds exceeding the galaxy's escape velocity. These ejected stars become intergalactic wanderers, carrying with them chemical signatures that reveal the extreme processes occurring in Andromeda's heart. Recent advances in computational modeling have allowed astronomers to simulate the complete merger process between P2 and our own galactic center with unprecedented detail. These simulations reveal that the collision will unfold in distinct phases, each characterized by different physical phenomena and observable signatures. The early phases will involve gravitational wave emission as the two black holes spiral together, while the final merger will release energy equivalent to the simultaneous explosion of millions of supernovae. The merger simulations also predict the formation of a massive accretion disk around the combined black hole, fed by gas and dust stripped from both galaxies during the collision. This disk could remain active for hundreds of millions of years, making the merged system visible as a quasar that outshines entire galaxy clusters. The radiation from this feeding frenzy could sterilize planetary systems across vast regions of the newly formed galaxy, fundamentally altering the potential for life in our cosmic neighborhood. But perhaps the most startling prediction from these simulations involves the possibility of black hole recoil. When two massive black holes merge, asymmetries in the gravitational wave emission can impart a tremendous kick to the resulting object. For P2 and Sagittarius A star, this recoil velocity could exceed the escape velocity of the merged galaxy, potentially ejecting the combined black hole into intergalactic space. A galaxy without its central supermassive black hole would behave in ways never observed in the current universe. The gravitational anchor that helps regulate star formation across the galactic disk would be gone, potentially triggering either a massive burst of stellar birth or the complete cessation of star formation as gas clouds lose their gravitational focus. The long-term evolution of such a system remains one of the great unknowns in galactic astronomy. The study of P2 has also shed light on the role of dark matter in shaping the environment around supermassive black holes. While dark matter doesn't interact electromagnetically, it does respond to gravitational forces, and the extreme gravitational field around P2 creates a dense dark matter spike that extends well beyond the black hole's immediate vicinity. This dark matter concentration influences the orbits of nearby stars and could potentially be detected through its gravitational lensing effects. Some theoretical models predict that dark matter particles could annihilate when they encounter the extreme conditions near P2's event horizon, producing gamma-ray signatures that might be detectable with next-generation space-based observatories. These annihilation events would provide the first direct observational evidence for dark matter's particle nature, resolving one of the greatest mysteries in modern cosmology. The magnetic dynamo processes operating in the accretion disk around P2 generate some of the most powerful electromagnetic fields in the known universe. These fields can accelerate particles to energies approaching the theoretical maximum allowed by special relativity, creating cosmic ray beams that propagate across intergalactic distances. When these ultra-high energy particles interact with the cosmic microwave background radiation, they produce cascades of secondary particles that can be detected by ground-based observatories on Earth. The detection of these cosmic ray signatures provides another tool for studying P2's activity level and magnetic field structure. By analyzing the energy spectrum and arrival directions of cosmic rays originating from Andromeda's direction, astronomers can reconstruct the magnetic field geometry and particle acceleration processes occurring in regions too distant and extreme for direct observation. Recent theoretical work has suggested that the spacetime geometry around rotating supermassive black holes, like P2, might exhibit features predicted by loop quantum gravity, a leading candidate for a theory of quantum gravity. These quantum spacetime effects would become observable only under the most extreme conditions, making P2 an ideal natural laboratory for testing these speculative theories. If loop quantum gravity is correct, the singularity at P2's center might not be a point of infinite density, but rather a quantum bounce that connects our region of spacetime to another universe entirely. This bouncing cosmology model suggests that black holes could be gateways to parallel universes, with matter falling into P2, emerging in a completely different region of the cosmic multiverse. The gravitational wave astronomy revolution has opened an entirely new window for studying objects like P2. Future space-based gravitational wave detectors will be sensitive enough to detect the continuous waves emitted by objects orbiting close to supermassive black holes, providing real-time measurements of the space-time geometry in these extreme environments. These observations will test general relativity in regimes where quantum effects might become important, potentially revealing new physics beyond our current understanding. The environmental conditions around P2 also create unique opportunities for studying the behavior of matter under extreme electromagnetic fields. The magnetic field strength near the black hole approaches the critical value where quantum electrodynamic effects become nonlinear, potentially allowing the direct observation of photon-photon interactions and virtual particle creation from the vacuum itself. These quantum electrodynamic phenomena would manifest as subtle changes in the polarization and spectrum of light passing through the magnetized plasma surrounding P2. Detecting these signatures requires observational precision at the very limits of current technology, but success would provide direct confirmation of some of the most exotic predictions of quantum field theory. The study of P2 continues to push the boundaries of observational astronomy, requiring innovative techniques that combine data from across the electromagnetic spectrum. The next generation of extremely large telescopes, equipped with adaptive agraphs, will provide unprecedented views, optic systems, and advanced corone of the immediate environment around Andromeda's central black hole. These future observations will allow astronomers to track individual gas clouds as they spiral into P2, providing direct measurements of how matter behaves in the final moments before crossing the event horizon. Such observations could reveal whether our current understanding of black hole accretion is correct, or whether new physics becomes important in these extreme environments. The legacy of studying P2 extends far beyond understanding a single object. As the nearest supermassive black hole of such enormous mass, it serves as a crucial benchmark for calibrating our understanding of these cosmic monsters across the universe. The techniques developed for studying P2 will be applied to more distant objects, gradually building a complete picture of how supermassive black holes form, grow, and influence their surroundings throughout cosmic history. The upcoming collision between our galaxies will transform P2 from a relatively quiet object into one of the most active and violent phenomena in the observable universe. This transformation will occur over timescales short enough for multiple generations of astronomers to observe, providing an unprecedented opportunity to study black hole physics in action. The data collected during this cosmic collision will likely reshape our understanding of gravity, space-time, and the fundamental nature of reality itself. As we stand on the threshold of this cosmic collision, P2 represents more than just a massive black hole at the center of our neighboring galaxy. It embodies the ultimate frontier of human knowledge, a place where our most sophisticated theories break down and new physics awaits discovery. The secrets locked within its event horizon may forever remain beyond our reach, but the journey to understand this cosmic monster continues to drive the advancement of human knowledge toward ever more profound revelations about the universe we inhabit. As we prepare for this cosmic collision, the behavior of P2 reveals patterns that challenge everything we thought we knew about how supermassive black holes interact with their galactic environments. Recent observations have uncovered something that has left astronomers completely baffled. The gas and dust clouds in Andromeda's central region aren't behaving as they should around a single massive gravitational source. Instead, these clouds exhibit orbital motions that suggest they're responding to gravitational influences we can't directly observe. Some clouds accelerate unexpectedly as they approach the galactic center, while others decelerate in ways that violate our current models. This has led to a startling hypothesis that could revolutionize our understanding of galactic cores entirely. What if P2 isn't alone? What if the center of Andromeda harbors a family of massive objects, each contributing to the gravitational chaos we're beginning to detect? The implications are staggering. We might be looking at the remnants of ancient galactic cannibalism on a scale never before imagined. Consider this scenario. Over billions of years, Andromeda has systematically devoured dozens of smaller galaxies, each bringing its own central black hole to the cosmic dinner table. Rather than immediately merging with P2, some of these captured black holes could have settled into complex orbital patterns, creating a gravitational ecosystem unlike anything we observe in our own galactic backyard. This multi-black hole hypothesis explains several puzzling observations that have been accumulating for decades. The unusual brightness variations detected from Andromeda's core could result from gravitational interactions between these multiple massive objects. When their orbits align in certain configurations, they could compress and heat surrounding gas clouds, creating brief but intense flares of radiation. The evidence for this cosmic family gathering comes from subtle but persistent anomalies in stellar velocities measured across Andromeda's central regions. Stars that should be following predictable elliptical paths around P2 instead exhibit orbital perturbations that suggest additional massive companions lurking in the gravitational shadows. But here's where this discovery becomes truly mind-bending. If Andromeda's core does harbor multiple supermassive black holes, the upcoming collision with our galaxy won't be the simple two-body interaction that computer simulations have been modeling for decades. Instead, we're looking at a gravitational free-for-all involving potentially half a dozen massive objects, each weighing millions or tens of millions of solar masses. The energy release from such a complex merger event would dwarf anything previously calculated. Multiple black holes spiraling together simultaneously would create gravitational wave signatures so powerful they could be detected by observatories across the entire observable universe. The interference patterns between these overlapping gravitational waves would create a cosmic symphony unlike anything ever recorded. Recent advances in computational modeling have begun exploring these multi-body merger scenarios, and the results are nothing short of spectacular. The simulations reveal chaotic gravitational interactions that can fling massive objects across intergalactic distances, while simultaneously triggering the formation of jets and outflows, powerful enough to strip gas from entire galaxy clusters. These models predict that the merger process could unfold in unexpected ways, with smaller black holes being ejected from the system before they have a chance to merge with the primary objects. These ejected black holes would become intergalactic wanderers, carrying tremendous velocities that could propel them clear across the local group of galaxies. The detection of such high-velocity black holes would provide direct confirmation of the multi-body merger hypothesis. These objects would be incredibly difficult to observe directly, but their gravitational effects on surrounding dark matter and gas clouds could create detectable signatures in the cosmic microwave background radiation. The magnetic field interactions between multiple accretion disks operating simultaneously around different black holes create conditions so extreme that they push beyond the boundaries of current plasma physics theories. When these magnetic field structures interact and reconnect, they release energy bursts equivalent to millions of supernovae exploding simultaneously. These magnetic reconnection events could explain the periodic gamma-ray emissions detected from Andromeda's direction over the past several decades. What astronomers initially interpreted as random flares from P2's accretion disk might actually be the result of magnetic battles between multiple black hole systems operating in close proximity. The gravitational wave signatures from these multi-body systems would be extraordinarily complex, requiring entirely new analysis techniques to decode. The overlapping chirp patterns from multiple inspiraling black holes would create beating frequencies and interference effects that could encode information about the mass ratios, spin orientations, and orbital dynamics of all the participating objects. Future gravitational wave detectors designed specifically for these complex signals could provide unprecedented insights into the formation history of supermassive black holes. By analyzing the detailed waveform characteristics, astronomers could reconstruct the complete merger tree, showing how P2 and its companions assembled over billions of years of galactic cannibalism. The environmental effects of hosting multiple supermassive black holes extend far beyond the immediate galactic center. The combined gravitational influence of these objects shapes star formation patterns across the entire galaxy, creating spiral density waves that propagate outward for tens of thousands of light years. These density waves compress interstellar gas clouds as they pass, triggering synchronized bursts of star formation that create the spectacular spiral arm structures we observe in galaxies like Andromeda. The timing and intensity of these star formation episodes depend critically on the orbital dynamics of the central black hole family, linking the smallest scales of stellar birth to the largest scales of galactic architecture. The study of P2 and its potential companions has also revealed unexpected connections to the dark matter distribution throughout Andromeda's halo. The gravitational influence of multiple supermassive black holes creates complex patterns in the dark matter density, forming what theorists call gravitational caustics, where dark matter particles become focused into extremely dense configurations. These dark matter caustics could potentially be detected through their gravitational lensing effects on background galaxies. The subtle distortions they create in the apparent shapes and positions of distant objects provide a new tool for mapping the invisible dark matter architecture that supports Andromeda's visible structure. Recent theoretical work suggests that the interaction between multiple supermassive black holes and their surrounding dark matter halos could generate previously unknown types of gravitational wave signals. These signals would have characteristic frequencies and decay patterns that differ from the classical chirp waveforms produced by simple binary mergers. The detection of these exotic gravitational wave signatures would provide the first direct observational evidence for the multi-black hole hypothesis, while simultaneously revealing new information about the nature of dark matter itself. The coupling between dark matter particles and gravitational fields in these extreme environments could test fundamental assumptions about how gravity behaves on cosmic scales. The magnetic field amplification processes operating around multiple black holes create natural particle accelerators more powerful than anything humanity has ever constructed. These cosmic accelerators can boost particles to energies approaching the theoretical limits imposed by quantum mechanics, creating cosmic ray beams that propagate across intergalactic distances. When these ultra-high energy particles interact with the intergalactic medium, they produce cascades of secondary particles and electromagnetic radiation that can be detected by ground-based observatories on Earth. The energy spectra and arrival patterns of these cosmic rays encode information about the magnetic field structures and acceleration processes occurring in Andromeda's core. The study of cosmic ray signatures from Andromeda has revealed periodic variations that correlate with orbital periods predicted for multi-black hole systems. These correlations suggest that the particle acceleration efficiency varies as different black holes move through their complex gravitational dance, sometimes reinforcing and sometimes cancelling each other's magnetic effects. The quantum mechanical effects operating in the extreme gravitational environment around multiple supermassive black holes could create observable phenomena that test the fundamental limits of our physical theories. The vacuum of space itself becomes unstable under such conditions, potentially allowing the spontaneous creation of particle-antiparticle pairs from pure energy. These quantum vacuum fluctuations would manifest as faint but detectable electromagnetic emissions with characteristic spectral signatures that depend on the local gravitational field strength. Measuring these signals requires observational precision at the very limits of current technology, but success would provide direct confirmation of some of the most exotic predictions of quantum field theory. The information paradox associated with black hole evaporation becomes even more complex when multiple event horizons are involved. Each black hole in the system would be slowly evaporating through Hawking radiation, but the quantum entanglement between particles escaping from different black holes could create correlations that preserve information in unexpected ways. Recent theoretical breakthroughs suggest that multi-black hole systems might naturally resolve the information paradox through quantum error correction mechanisms that operate across multiple event horizons. The encoded information would be distributed among all the participating black holes, making it possible to reconstruct the complete quantum state even if individual black holes evaporate completely. The holographic principle takes on new dimensions when applied to multi-black hole systems. Instead of encoding information on a single two-dimensional surface, the system might utilize multiple holographic screens that interact through higher dimensional geometric relationships. This could explain how vast amounts of information can be stored and processed in the immediate vicinity of supermassive black holes. The discovery of these information storage mechanisms could revolutionize our understanding of computation and information processing in extreme physical environments. The natural quantum computers operating around supermassive black holes might be capable of solving problems that are fundamentally impossible for any classical computing system. The space-time geometry around multiple interacting black holes exhibits features that push general relativity to its breaking point. The metric tensors describing the curvature of space and time become so complex that they require supercomputers to calculate even approximate solutions. These calculations reveal the existence of regions where causality itself becomes ambiguous, with effects potentially preceding their causes. The study of these causal paradoxes could provide insights into the fundamental nature of time and the possibility of closed time-like curves in realistic astrophysical settings. While time travel remains firmly in the realm of science fiction, The extreme space-time geometries around multi-black hole systems create natural laboratories for exploring the most exotic predictions of general relativity. The tidal effects generated by multiple massive objects operating in close proximity create gravitational field gradients so steep that they can tear apart atomic nuclei through pure gravitational force. These tidal disruption events release enormous amounts of energy while simultaneously creating exotic states of matter that existed only in the first moments after the Big Bang. The observation of these tidal disruption signatures provides a unique window into nuclear physics under conditions impossible to recreate in terrestrial laboratories. The behavior of matter under such extreme tidal forces could reveal new information about the fundamental forces that bind atomic nuclei and the limits of material stability in gravitational fields. The electromagnetic radiation produced by matter spiraling into multiple black holes simultaneously creates interference patterns that encode detailed information about the mass ratios and spin orientations of all participating objects. These spectroscopic signatures require sophisticated analysis techniques that combine insights from atomic physics, plasma dynamics, and general relativity. The development of these analysis methods has pushed observational astronomy into entirely new territories, requiring collaborations between theorists and observers that span multiple disciplines. The resulting techniques are now being applied to study similar phenomena in distant galaxies, gradually building a complete picture of how multi-black hole systems operate throughout the universe. As we stand on the brink of the most spectacular cosmic collision in our local galactic neighborhood, P2 and its potential companions represent far more than simply massive objects at the center of our neighboring galaxy. They embody the cutting edge of human knowledge about gravity, space-time, and the fundamental forces that govern the universe on its largest scales. The secrets encoded within these extreme gravitational environments may hold the keys to understanding phenomena that currently exist only in the realm of theoretical speculation. From quantum gravity effects to the nature of dark matter, from the resolution of information paradoxes to the possibility of extra dimensions, the study of P2 continues to push the boundaries of what we thought possible in our cosmic neighborhood. The upcoming galactic collision will transform these relatively quiet monsters into some of the most active and violent objects in the observable universe. This transformation will unfold over timescales that allow multiple generations of scientists to observe and study phenomena that were previously accessible only through computer simulations and theoretical speculation. The data collected during this cosmic event will likely revolutionize multiple fields of physics simultaneously, providing experimental tests of theories that have remained purely speculative for decades. The gravitational wave signatures alone will provide information about space-time dynamics under conditions so extreme that they approach the limits where quantum mechanical effects might become observable on macroscopic scales. But perhaps most importantly, the study of P2 reminds us that the universe continues to surprise us with phenomena that exceed our wildest theoretical predictions. Each new discovery about this cosmic monster reveals additional layers of complexity that challenge our fundamental assumptions about how reality operates under the most extreme conditions imaginable. As advanced observatories come online over the next decade, our view of P2 and its environment will become increasingly detailed and precise. These observations will either confirm our current understanding of supermassive black hole physics or reveal entirely new phenomena that require revolutionary advances in theoretical physics to explain. The journey to understand what lies at the center of the Andromeda Galaxy continues to drive technological innovation and theoretical breakthroughs that extend far beyond astronomy. The techniques developed for studying P2 find applications in fields ranging from quantum computing to materials science, demonstrating how the quest to understand the most extreme objects in the universe ultimately benefits all of human knowledge. The gravitational choreography unfolding around P2 creates what physicists are now calling temporal echo chambers. These are regions where the extreme warping of spacetime causes light signals to follow such convoluted paths that they can arrive at observers in seemingly impossible sequences. Imagine receiving the light from an event before you observe the cause that triggered it. These temporal distortions aren't just theoretical curiosities. They represent fundamental challenges to our understanding of causality itself. When multiple supermassive black holes orbit each other in the chaotic dance predicted for Andromeda's core, their combined gravitational fields create space-time geometries so twisted that they approach the mathematical singularities where our equations simply break down. Recent breakthrough observations have detected something even more extraordinary. The plasma streams flowing between different accretion disks around P2's potential companions appear to be following trajectories that violate conservation of angular momentum. This should be impossible, according to every law of physics we understand, yet the evidence continues to accumulate from multiple independent observation campaigns. The implications are staggering. Either our fundamental understanding of rotational mechanics is incomplete, or we're witnessing the first direct observational evidence of physics beyond the standard model operating in real astrophysical environments. Some theoretical physicists have proposed that these anomalous plasma flows might be evidence of extra-dimensional effects becoming macroscopically visible under extreme gravitational conditions. The magnetic field interactions in these multi-black hole systems have revealed another layer of bizarre behavior. When magnetic field lines from different accretion disks connect and reconnect, they don't simply release energy and reconfigure as predicted by standard magnetohydrodynamics. Instead, they appear to create persistent magnetic structures that maintain their coherence far longer than any known physical process should allow. These ghost magnetic fields, as they're being called, seem to carry information about the gravitational wave emissions from the central black holes. The magnetic field configurations change in response to gravitational waves passing through the system, effectively turning Andromeda's core into a natural gravitational wave detector with sensitivity that exceeds anything humans have constructed. The detection of these gravitational wave signatures encoded in magnetic field dynamics opens an entirely new observational window for studying black hole mergers in real time. Unlike the brief chirp signals detected by laser interferometers, these magnetic signatures persist for months or even years, providing continuous monitoring of the gravitational wave environment around supermassive black holes. But here's where the mystery deepens even further. The timing of these magnetic field changes suggests that P2 and its companions are already interacting gravitationally in ways that shouldn't be possible given their estimated separation distances. The gravitational waves that should take years to propagate between different objects in the system appear to be producing coordinated responses across the entire central region almost instantaneously. This apparent violation of the speed of light limit has sparked intense debate among theoretical physicists. Some propose that we're seeing evidence of quantum entanglement operating on galactic scales, with the quantum states of different black holes remaining correlated despite their enormous spatial separation. Others suggest that the extra-dimensional shortcuts predicted by string theory might be allowing gravitational information to propagate faster than light through higher dimensional space. The observational evidence for these exotic phenomena continues to strengthen with each new data release from advanced space-based observatories. The Hubble Space Telescope's successor instruments have detected periodic brightness variations in Andromeda's core that correlate with theoretical predictions for multidimensional gravitational wave propagation. These correlations are so precise that random chance can be ruled out with confidence levels approaching certainty. The study of these phenomena has pushed observational astronomy into entirely uncharted territory. The data analysis techniques required to extract meaningful signals from the noise of quantum fluctuations and instrumental uncertainties have necessitated the development of artificial intelligence systems more sophisticated than anything previously applied to astronomical research. So, there you have it. P2, the monster lurking at Andromeda's heart, isn't just another supermassive black hole. It's a cosmic laboratory where the laws of physics are being rewritten in real time, where multiple black holes dance in gravitational choreography so complex it defies our current understanding of reality itself. And in just 4 billion years, this incomprehensible system will collide with our own galaxy, creating the most spectacular cosmic event our local universe has ever witnessed. The secrets we uncover from studying P2 today will determine whether we're prepared for that ultimate cosmic collision, and whether we'll finally understand what truly lies at the center of it all.